An example for thermal expansion. Question: a copper wire of 15 meter long is cooled from 40 to -9 degrees Celsius. How much change in length of this copper wire? And given the coefficient of thermal expansion, the alpha L. Okay, let's check how are we going to solve this. So this is the equation, the previous equation that we're going to use. So in this question, we are asked to calculate the delta L. So you know your alpha, you know your L naught, which is 15 meter, and you know your delta T, which you can calculate the difference from here. And you just substitute all the values, you will get your delta L. As simple as that. Another one, a 0.1 meter rod of a metal elongates at 0.2 millimeter. This is the delta L, right? On heating from 20 to 100 degrees Celsius. And also given here is the delta T. Determine the value of the linear coefficient of thermal expansion. So they are asking for you to calculate what is the alpha in this case. And you know that you can use this equation to calculate your alpha. So you know your delta L, you know your L naught, and you know your delta T. And very simple, you can work out your coefficient of linear expansion. Next, we have thermal conductivity. Okay, so thermal conduction actually can be defined as the ability of a material to transport heat from high to low temperature regions of that material itself. And the property that actually characterizes this thermal conduction is what we call as thermal conductivity. So this thermal conductivity is a property that characterizes the thermal conduction process. So this thermal conductivity, it can be defined in terms of this expression, Q equals to negative K dt over dx, also known as Fourier's law. So Q here actually is the heat flux or the heat flow. You can call it also heat flow per unit time, per unit area. And this area is taken at that perpendicular to the flow direction. So K is the thermal conductivity. This is K, thermal conductivity. And dt over dx is the temperature gradient through the conducting medium. So the units of Q and K are, this is the units, all right? Or it is also can be represented as watts per meter squared for heat flux, and this one is watts per meter Kelvin. And the minus sign here, actually it indicates the direction of heat flow is that from hot to cold, or actually down the temperature gradient. All right, let's look at an example here that relates the thermal conductivity. Calculate the heat flux through a sheet of steel which is 10 millimeter thick if the temperatures at the two faces are 300 and 100 degrees Celsius. So they ask you to assume this process is happening at steady state. So the thermal conductivity for steel, we can actually find it in given references, which is 51.9 watts per meter Kelvin. So you can use this equation to work out what is the Q. So K is known, delta T is known, delta X also is known. All right, so this is delta X. Delta X. So you just substitute all the values and you will get your answer. And this is the comparison of thermal conductivity according to all the materials. Metals have highest conductivity compared to ceramics and polymers have the lowest thermal conductivity. So the energy transfer mechanism in metals is through atomic vibration and motion of free electrons. And in ceramic, the mechanism of the energy transfer in thermal conduction is just atomic vibration. And for polymers, it's vibration and rotation of chain molecules. So the higher the thermal conductivity of a material, it means that material tend to have higher thermal conduction. Okay, it can transport heat from high to low temperature regions of a substance higher compared to ceramics or polymers. Next, I'm going to talk about thermal stresses. So thermal stresses, they are stresses induced in a body as a result of changes in temperature. So materials also experiences stresses, not only us, not only the human, materials also. Okay, so the materials tendency, how do they express their stresses? By expanding or contract, either expand or contract. So if a heated or cool material is restrained to its original shape, the thermal stresses will develop within the material. So the stress in a material can be calculated using this formula here. So this is stress, okay? Engineering stress equals to E. What is E? E is the modulus of elasticity or the Young's modulus. Alpha L is the linear coefficient of thermal expansion, and delta T is just the change in temperature. So when you have your modulus of elasticity, you know your change in temperature, you know your thermal expansion coefficient, you can calculate your stress, engineering stress. All right, that's all. Thank you for watching.